In this video, we'll learn about how to do a complexity analysis of recursive function. We'll look at the two types of recursive functions. We'll look at reduce and conquer recursive functions, and we'll do complexity analysis first, and then we'll look at the divide and conquer recursive functions, and then we'll do complexity analysis for this type of recursive functions as well. So let's look first at the reduce and conquer recursive functions, and we'll see how we do complexity analysis for these type of recursive functions. What you need to do with complexity analysis for recursive functions is that you basically will need to set up a mathematical analysis for the worst case scenario. The first things you basically have to do is to identify what's the algorithm's basic operation. And if you remember from previous videos, the basic operation is the heaviest operation that the function is doing. The second thing you need to do is look at the base case and at the general case and find what's the number of basic operation that's done in the base case and in the general case. Notice that in the general case you will end up with something we call the recurrence relationship. The third thing you need to do is you solve the recurrence relationship so that you can obtain a closed form or estimate the order of magnitude of the solution. And we'll see that one later when we are looking at the master method theorem. So we're going to see an example of how do we do the complexity analysis in a second. But the important thing you need to keep on your mind is to decide on what's the basic operation, what's the heaviest operation that the algorithm is doing, and then look at the base case and in the general case and solve them, compute the number of basic operations for the base case and the general case, and then we use either forward or backward substitution or the master method theorem to basically solve the recurrence relationship. So if you look at this example here where we are computing the factorial of a number n, remember just the factorial of a number n is if the number is 1, which is its factorial is 1. If the number is different from 1, if the number is n in general, its factorial is n times factorial of n minus 1. So the base case is when n is equal to 1. The general case is when n is not equal to 1. If you look at this algorithm here, you could see that the heaviest operation that this algorithm or this function is doing is multiplication. So we can consider multiplication as the basic operation. And then the objective when doing complexity analysis is to count how many times this algorithm is doing multiplications. So if we look at the factorial functions and we say what's going to be the basic operation, we know that it's multiplication. If we're going to look at what's the number of basic operations that's done in the base case, so if you look back again, you could see that in the base case, I'm not doing any multiplication. However, I'm doing multiplication in the general case. And as well, you could see that the number of basic operations that recursive factorial is done to solve a problem n is the number of basic operations that's required to solve a problem of n size of n minus 1 plus 1 extra basic operation. So if the basic operation is multiplication, in the base case when n is equal to 1, I'm not doing any multiplication, so c of 1 is 0. The number of basic operations when the input to the function is 1 is 0. However, to compute the factorial of n, the number of basic operations that to do that is going to be the number of basic operations to compute factorial of n minus 1 plus extra 1. We're going to see how we can solve this relationship. C1 is equal to 0 and C of n is equal to C of n minus 1. We call that a recurrence relationship. The objective is to convert of C of n is equal to C of n minus 1 plus 1 and C of 1 is equal to 0 and compute what we call basically a closed form what's the value of C of n in terms of n. So C of n is equal to C of n minus 1 plus 1. We call that a recurrence relationship. But when we have C of n is a function of n, like in this case here we have C of n is n minus 1, we call that a closed form. If you look at this example here, C of n was computed to be n minus 1, which in terms of O, it's basically O of n. It's very important to differentiate between the recurrence function and the recursive functions, and then the recurrence relationship between C of n and C of n minus 1. If you look at factorial, this recursive function gives me f of n is equal to 1 if n is equal to 1, while f of n is f of n minus 1 times n for any n bigger than 1. However, the recurrence relationship is the following: C of 1 is equal to 0 and C of n is C of n minus 1 plus 1 for the general case. So always be careful to differentiate between what's the recursive function is about and what's the number of basic operations that's expressed as the recurrence function. Now, how do we solve recurrence relationships? If you look at the example here, if we have C of n is equal to C of n minus 1 plus 1 and C of 1 is equal to 0, we're going to look at how do we solve this one using two approaches, either forward substitutions or backward substitutions. If we are using forward substitutions, the idea is to take C of n, we have C of n is equal to C of n plus 1. You compute what's C of n minus 1 using the original formula. You'll find that C of n minus 1 is equal to C of n minus 2 plus 1. C of n minus 2, again using the original formula, it's C of n minus 3 plus 1. You keep doing that until you reach to C of 1, which is already defined as equal to 0. Now you start again by putting C of, now that you know the values of all the terms, C of n minus 1, C of n minus 2, you start again with the original formula, where you get C of n is equal to C of n minus 1 plus 1. But what's C of n minus 1? We just wrote it down here that C of n minus 1 is equal to C of n minus 2 plus 1. So you replace C of n minus 1 with its value in terms of C of n minus 2. And again, you replace C of n minus 2 with its value with C of n minus 3. Notice that every time I'm doing one replacement, I'm adding plus 1. So when I'm done with the substitutions, I will reach the bottom, which is C of 1 plus 1 plus 1 plus 1 plus 1, and there are n minus 1 ones. However, the value of C of 1 is equal to 0. So the total number of ones I have is n minus 1. So in this case, C of n is going to be equal to n minus 1. And we call this the closed form. In terms of complexity, if you have C of n is n minus 1, this is O of n. Now, if we are doing backward substitution, that's when we start from C of 2, C of 3, C of 4, until we get up all the way to C of n. So remember, if I have C of n is equal to C of n minus 1 plus 1 as an example, and C of 1 is equal to 0, I can go and say, hey, what's C of 2? C of 2, according to my formula, is equal to C of 2 minus 1, which is 1 plus C of 1 plus 1. However, C of 1 is equal to 0, so C of 2 is going to be equal to 0 plus 1, which is 1. C of 3 is C of 2 plus 1, according to the original formula. But C of 2, I just computed it, which is equal to 1, plus 1 is going to be equal to 2. C of 4 is going to be equal to C of 3 plus 1, which is 2 plus 1 plus 3. You could see the relationship between C of 4 is equal to 3, C of 3 is equal to 2, C of 2 is equal to 1. So generally speaking, you will see that the relationship that C of n is going to be n minus 1, which is again O of n. Now, if we look at the time complexity for divide and conquer approach, we use a general formula which is called the master method to solve the time complexity for divide and conquer functions. The general approach is that if you have a recursive function and we can find the recurrence relationship for the recursive function is in the following form, where C of n is equal a C of n over b plus f of n, where f of n has a complexity of O of n of k. Then if a is less than b to the k, so we take a and we compute b to the k, and we see if a is equal, if less than b to the k, then we can say that C of n is O of n to the k. If a is equal b to the k, then C of n will be O of n to the k log n. However, if a is bigger than b to the k, then C of n is going to be O of n log base b of a. What does that mean when we have C of n is equal a of C of n over b plus f of n? Remember that this is the divide and conquer approach. So the general idea is that if we take a problem of size n and we divide it into a problems, and each one of them is n over b. However, to divide the problem and then to combine the solutions, it's gonna cost me f of n basic operations. Just to give you a few examples, assume that you find that the recurrence relationship is C of n is equal to of C of n over 2 plus n. So in this case, a is gonna be 2, b is 2, f of n is n. And in this case, since f of n is n, O is gonna be k is gonna be equal to 1, since f of n is equal to n, which is basically O of n to the power 1. But since a is equal to b to the k, then C of n is gonna be O of n log n according to the second condition. Let's look at another example. C of n is equal to C of n over 2 plus 1. In this case, a is going to be equal to 1 and b is equal to 2. However, f of n is equal to 1, and since f of n is equal to 1, basically it's going to be O of 1. So k will be 0 in this case. But since a is equal b to the k, which means that C of n is O of n to the k log of n. But n to the k is n to the 0, which is 1 log n, 1 log n. So in this case, C of n will be O of log n. If we look at the third example, where C of n is equal to 3 C of n over 2 plus n, in this case, a is going to be equal to 3, b is going to be equal to 2, and f of n is equal to n, which is O of n, so which makes k is equal to 1. But since a is bigger than b to the k, then C of n will be O of n to the power log of base b of a. So in this case, C of n is going to be O of n log of a, log base of a, log a of, which is basically log 3 base 2. Another fourth example, if C of n is equal a C of n over 2 plus n squared plus n minus 100. And you could see that f of n in this case is basically the terms n squared plus n minus 100, which is make it O of n squared. So in this case, k is going to be equal to 2. So a is equal to 8, b is equal to 2, and k is equal to 2. What's going to be a? which is 8, and b to the k, which is gonna be equal to b to the k is gonna be equal to 4. So in this case, you're gonna see that a is gonna be bigger than b to the k, which makes it basically O of n log 2 of 8.